Welcome students. In this class we are going to talk about the wave equation but in even dimension. So higher even dimension, what I meant is n is greater than equal 2. So wave equation in even dimension. So n equals to, let's say, 2m, clear, m equals to 1, 2, dot, dot, dot. So essentially we want to generalize the idea, the formula, the Poisson formula, which we have derived for n equals to 2, right? So up till now what we have seen, let us recall from the up till the last video, what we have done is, for n equals to 1 we got the D'Alembert, right? D'Alembert's formula, which is the most fundamental formula. See, now in all of this we are only concentrating on homogeneous problem. Why? Because we know that once we get a solution of the homogeneous problem in any dimension, what we can do is then use Duhamel's principle, okay, to find out the solution for the non-homogeneous problem. So we are only interested in finding the solution for the homogeneous problem. So n equals to 1, D'Alembert's formula give you the solution. Okay, now n equals to 2, we are not going from n equals to 1 directly. Okay, so what we are going to do, we did n equals to 3, and for that we provided something called the Kershaw's formula, right? Kershaw's formula, and then from there we use the method of descent, right? Method of descent. So basically we thought of the function as independent of one variable, and and we deduced the solution for n equals to 2, which is the Poisson formula, right? Okay, now in last class what we did, we basically generalized the idea of Kershaw's formula for n, which is 2m plus 1, clear? So for m equals to 1, 2, so this is what we did. So basically we looked at in the higher dimensional wave equation but in odd dimensions. Yeah, today what we are going to do is, so this is in odd dimension. So now what we are going to do, we are going to look at the higher dimensional wave equation but in the even dimension, clear? So first of all, again if you recall that we started out with some okay, so let me start with the problem and then we can go from there. So the equation utt minus Laplacian of u, this is equals to 0 in Rn cross 0 infinity, clear? U is at the point x0, that is equals to, let's say, g of x, that is given to us. So again only homogeneous problem, okay, and u t at the point x0 is given by h of x, clear? H of x, and this is in Rn cross t equals to 0, clear? Okay, now what we want to do, we want to look at the even dimension problem that okay, now so this n, yeah, one simple thing, this n is even, yes, that is what we assume. So n is even, so assumption we already wrote, but anyways let me put it here properly. N is an even integer, so of course this is greater than equal to, clear? So n is an even integer, and so basically we think of there is a solution, right? And then we find out what u is in terms of g and h, right? So let's call that as 1. So let u in Cm, okay, so the regularity of u is Cm, okay, is the solution of 1, okay, for m equals to n plus 2 by 2, clear? So see, in 2 dimensions, let's say n equals to 2, you have 2 plus 2 by 2, which is 2, right? So m equals to 2, so basically you need u to be in C2 in 2 dimension, clear? Okay, and as you go higher dimension, that is the regularity which you need. So basically we start out with u, which is this, so in Cm, right? Okay, now we want to put a representation formula as we have already done, and for that what we are going to do exact same sort of idea, yes, the method of descent. So we define, so set u bar of x1, x2, xn plus 1 t. This we set it to be u of x1, x2, xn t, right? One variable is missing here. You remember in 3 dimension from 3 to 2 when we went, we wrote it like this. So u bar of x1, x2, x3 and t was u of x1, x2 and t. See, this u we already know. 2 dimension, when we were solving for 2 dimension, we assume that we know the solution in 2 dimension, which is given by u. Right. Now I am defining a 3-dimensional function u bar using u such that u is independent of the third variable. U bar is independent of the third variable, right? Okay, and then you use the Kershaw formula in 3 dimension. Okay, use Kershaw's here, and then you go down to 2 dimension. That's the idea, right? The method of descent. This is due to Hadamard. Please remember, this is called Hadamard's method of descent. Clear? Okay, now when you set something like this, so here also I am doing the exact same thing but just in higher dimensions. Yes, okay. So this is in, of course, Rn plus 1, right, cross 0 infinity. Clear? Okay, and what is the initial condition? The initial condition is u bar equals to g bar, okay, and ut bar equals to h bar, okay, on Rn plus 1 cross t equals to 0. Okay, so here, of course, where you remember g bar, how did we define g bar of x1, xn plus 1 is given by g of x1, x2, xn, and h bar of x1, x2, xn plus 1, that is defined by h of x1, x2, xn. Okay, so you see, we know already what u is. G and h is given to us. We are defining a new capital U bar, capital G bar, not U, capital U bar, U bar, G bar and H bar using U, G and H, right? So as n is odd, okay, we have the formula, you remember last video we have derived, okay. So now what we are going to do is we are going to use that same formula. So we fix a x in Rn, okay, t greater than 0, and we write x bar to be x1, x2, xn 0, right? This is in Rn plus 1. Clear? So we're just writing one x bar like that. So x bar, whenever I am saying, it is in t equals to 0 space. Okay. So basically, not t equals to 0 space, xn plus 1 part is 0. Okay, right. And what we have is, if you write u of xt now, okay, u of xt. So from Kershaw formula, yes, you remember Kershaw formula, I hope, that is given by 1 over gamma at the point n plus 1. If you remember that gamma, that is 1.3 factor, 1.3.5, that particular number, okay, given and this is evaluated at del t, okay, 1 by t del t. Okay, I am just using the formula. Again, there is no need of remembering this formula. Okay, if you are given in the examination to work out this formula, then the formula will be provided to you. Okay. Of course, you should know the subtle details about the formula, and which we are going to explain to you, which we should know. I am not expecting you to remember the exact formula, but some details should be known about what is so special about this formula in 3 dimension or 2 dimension. G bar ds, clear? So that is there, plus 1 by t del t whole power n minus 2 by 2 t power n minus 1 del b bar x bar t, okay, h bar ds bar, okay, and then we will close the. So this is there, and what is b? So essentially here b x bar t, this denotes the ball in Rn plus 1, okay, with center x bar, and radius t, okay. Of course, what is d of s bar? That denotes the surface measure, if you want to put it properly. Otherwise, you know, it is just the surface element, okay. D of s bar, that measures the surface. So basically, this is the surface measure. If you do not know the measure, think of this as a surface element on the del b bar x bar t, okay. Surface measure on del b bar x bar t, clear? Now see here, I want to calculate some particular terms here, right? This is exactly what we did in the n equals to 2 case, so I am not going to explain every single detail here. That is always understood from the other part, okay. So this is just an in higher dimension, del b bar x bar t, okay, g bar ds bar. This particular quantity I want to calculate. So this quantity can be written as 1 by c. First of all, the surface area of this particular ball, okay, that is given by, so this is in which dimension? If you remember, n plus 1 dimension, okay. So that is why this is n plus 1 alpha n plus 1, okay, t power n, okay, right. Here let me let me write it down, and I will explain to you what I meant by this. Do not get confused here with this notation. See, what is alpha n plus 1? This is the volume of the unit sphere, unit ball or sphere, whatever you want to call it, okay, in Rn plus 1. So basically Sn, okay, unit ball. So radius is 1, Sn, okay, that is the volume. So alpha n plus 1, it's not like alpha multiplied by n plus 1, okay. So as I told you, alpha n is that the volume of the unit sphere, okay. Alpha, so S2, let's say alpha 3 if I am writing, so basically that is the volume of S2, okay. So here 1 by n plus 1 times alpha n plus 1 t to the power n. This is just the, you know, the how do I put it, the surface area of the sphere here, right? That is what it meant, right? Okay, now that is actually, now if you want to calculate this thing, I think you guys can handle it here. You can just write it like 2 by n plus 1. Let me explain to you how it is coming. T power n, okay, 2, why? Because you see again the same thing here. I am doing it on the whole ball, the outside shell actually, but the whole ball, right? So something like this. Now you see there is a upper part and there is a lower part, clear? Okay, so in the upper part and lower part, so there are two hemispheres, okay. Not in this is in higher dimension, but you do realize that we can't draw the higher dimension. This is just for n equals to 3. It is easy to visualize, that's why I'm drawing, okay. So that is why, I'm just so basically I'm using the symmetry, and I am just taking twice each hemisphere. Okay, so basically this integral is 2 times the integral in each hemisphere, right? Okay, so that will be, you remember that surface integral, we did that formula, so we are using the same thing here. Okay, so we are coming from let's say some certain volume element here, so certain surface element here, and I am projecting it to something over here, right? Okay, so what happens, if you remember, this can be written as g of y, because on the ball b xt in the lower dimension, just in this dimension. See, the integral is happening here, integral is happening here, okay, integral is happening here, but the thing is, what we are doing is we are basically projecting it in this dimension, kind of. Okay, we are projecting it in this dimension, and that is why so basically that is why I am writing it on bx. So basically in the whole this place, you understand this sort of thing. Let's say we are projecting it here, okay, and of course, what is the graph of this the sphere, the upper sphere, hemisphere, basically what is the graph of this thing, you see so basically that will be given by gamma y, which is this is just t square minus mod y minus x square whole power half, right? Okay, the graph of this function. So basically the upper half is a graph of that function, right? So basically the upper half will be del b bar xt, clear, del b bar xt intersection y n plus 1 is greater than equal 0, right? This upper half, that upper half is essentially the graph of this function, graph of gamma, right, where gamma is this. I hope this is fine. The upper hemisphere is basically del b bar intersection y n plus 1 greater than equal 0, right? And this upper half can be written as this one, right? That the graph of gamma, where gamma is that this t square minus mod y minus x square whole power half. Okay, so that's not very difficult to see. Okay, so what is the when we do this change of variable, what do we get? We get essentially here 1 plus gradient gamma y square whole power half dy. Clear? That's what we get. Okay, right. Now what we are going to do is we are going to simplify it a little more. Integral over del b bar x bar t, okay, g bar ds bar, this particular thing is given by, we will write it like this, 2 n plus 1 alpha n plus 1 t power n, clear, integral over bxt, okay, and I will just replace whatever, I will just replace this particular, see, gamma t is this one, right? So we'll just calculate this thing and replace it, and I can skip the calculation, I think. Yeah, that is quite evident. Okay, it's not very difficult to calculate, of course. T square minus y minus x square whole power half dy. Clear? Okay, now this if we want to put write it properly in terms of the average, that will give us 2t alpha n by n plus 1 alpha n plus 1 average of bxt, okay, g of y by t square minus y minus x square whole power half dy. Okay. Okay. Why is this happening? Because you see 1 plus gamma, this particular thing, if you calculate 1 plus gradient gamma y square whole power half, that is actually t times t square minus y minus x square whole power half. Okay, so reorganized everything and put it together. Okay, so that's why they are there. Why is this alpha t coming? Because you see b of xt is in Rn, right? So basically I need to, when I am taking the average, I need to get that alpha n accommodated, right? That is why this alpha n is there. Okay, right, so that is there. Now I think I missed a t somewhere, no? I think this t should be here, no? No, that's fine. Yeah. So this t is not there. It's fine. Yeah, it's fine. There is a t here, but that will get accommodated with t power n. So that is why t power n minus 1 is gone. Okay. Right. See here there is 2t because of this t. This 2t is there and t power n plus 1 is there, but that is getting cancelled. That is why t power n. But again, when I am getting it to be b of xt, there t power n is there. That's why this t is again coming back. Okay. So I mean, this is just a one line calculation. If you want, you can just verify it. That's not a issue. Okay. So therefore, if you just put all of this together, what you get is u of xt is given by 1 by, so this is a slightly, not slightly, this is a big formula. Okay, so please bear with me here, and we do not have any other option but to write it down. Okay, this one n plus 1 alpha n plus 1, okay, and del t of 1 by t del t, okay, power n minus 2 by 2 t power n integral b of xt g of y. I'm just writing this part down, g of y by t square minus y minus x square whole power half, okay, dy plus 1 by t del t whole power n minus 2 by 2 t power n, the average of bxt, okay, h of y by t square minus y minus x square whole power half, okay, dy. Clear? Okay. So here, of course, you remember gamma n plus 1 is 1 dot 3 dot, so 1 multiplied, of course this is, yeah, times n minus 1. Okay, and what is alpha n? Alpha n is given by alpha n, as I told you, this is just the volume of the unit ball, okay, unit sphere or whatever you want to call it. Yeah? So this is pi n by 2 by the gamma of gamma function. This is n plus 2 by 2. Okay, in higher dimension, I'm just explicitly writing it down. I mean, there is no special need. Okay, and of course, if you want to calculate, you can calculate gamma n also. That's not a point. But anyways, so where gamma n is given by this. Clear? Okay. So now, if I put everything together, yes, what is the representation formula in event dimension? Let me write it down. The representation formula. So you see, we are not doing anything special here. Yes, so exactly the same sort of thing, just calculating some particular terms. So the for n even, okay, for even n, u of xt that is given by 1 by gamma n, okay, 1 by gamma n del t, one sec, del t, okay, 1 by t del t whole power n minus 2 by 2, and then you have t power n, the average of bxt, okay, g of y by t square minus y minus x square whole power half, okay, dy plus 1 by t del t whole power n minus 2 by 2 t power n, the average over bxt, okay, h of y by t square minus y minus x square whole power half, okay, dy. So this is when n is even and gamma n is 2.4 dot, it goes on like this, n minus 2 dot n. Okay, so how did I come from 1 by gamma n? So you see here it is 1 by gamma n plus 2 times this thing, right? So I you do some calculations here. Okay, you do some calculations here, and then after some calculations you can this because this alpha n plus 1 is there, n plus 1 alpha n plus 1 is there. So all of this, if you accommodate properly, so if you just write it down explicitly, you are going to get 1 by gamma n. That's what I am trying to say here. And then you have this, and of course you can check that when gamma 2, so of course gamma 2 is will give you back your Poisson's formula. Clear? Okay, now one so what is the existence theorem here? Let me write down the theorem, the existence theorem. So this is the important bit. This is what we actually proved. So what we actually proved, let me write it down. Okay, so assume, so let's call this formula as a star formula for this video. Okay, assume n is even integer greater than equal to clear, and g is in Cm plus 1 Rn, clear, h is in Cm of Rn for m equals to, if you remember, even, right, n plus 2 by 2. Okay, now if u is defined by star, okay, then number one, you see u of course is in C2 of Rn cross 0 infinity. Clear? So basically u will be in C2. If you define g to be in Cm plus 1, h to be in Cm, what the u which we are going to get, that is definitely going to be in C2, provided you see why, because I mean the formula actually gives, if g is in Cm plus 1, the integral of g will be, I mean if you do this part, this as a function of t, this particular thing as a function of t will be Cm plus 2, and after that you have to accommodate this particular derivatives, one derivative here and this n minus 2 by 2 times this d of this derivative here, that also has to accommodate, and once you do that you can see that u is in C2. So this is not a very difficult thing to do. Okay, so please do that part. Yes, so u is in C2, of course utt minus Laplacian of u equals to 0, that has to be the case in Rn cross 0 infinity. Okay, sorry, Rn cross 0 infinity. Clear? And of course, how is the boundary condition satisfied? It is satisfied in terms of limit. Yeah, I am not proving all this because this is exactly the same sort of thing which we are doing up till now. Okay, so there is nothing special here, exactly the same thing. Once you have this formula, you can just calculate because you have an explicit formula here, right? That is so special about wave equation. You have explicit formulas here for the homogeneous problem and the non-homogeneous problem, of course. Okay, so you can just check whether things are working out or not. That's all. Okay, so you see ut of xt, if you calculate, that is going to be h of x naught. Yeah. So this is for every x naught in R. Yeah. Okay. So I am not going to the proof. I am skipping. Yeah. Proof. Please check yourself. Check yourself. Okay. Right. So now a small thing which I want, not small thing. It's an important one, but I want you guys to understand what is happening here. See, if you look at this formula, the star, okay, for this what I need to do is maybe I have to, okay, so let's start with this formula first and then we'll go back to the other one. See, if n, I think it is better if I write down the two formulas, okay. See, for n even, let's just look at n even, just from a mathematical point of view. Just let us look at the n even thing. Okay, you see the data, the solution u, okay, depends of course on g and h. Clear? As in D'Alembert also we have seen the solution depends on g and h. Clear? U depends on g and h. Okay, but in even dimension, you see this g, you have to know what g does in the whole ball bxt. Clear? Again, you have to know what h does in the whole ball bxt. Okay, this does not seem much, but this is very important. So you need the information, right? If you want to find the solution, you need the information on g and h. What are g and h? Those are initial data. So you need the information on initial data in the whole ball b of xt, right? On the whole ball b of xt. Okay, now if you compare this thing with, so this is for the even dimension. Okay, we'll explain what all of this means in the physical sense, but I mean let's write down the odd dimensional the Kershaw formula. Okay, so you see in odd dimension, in I mean I wrote somewhere in odd dimension, no, the formula here. You see, but in odd dimension the Kershaw formula is given like this. Okay, you see in odd dimension, so essentially here what will happen is this. You see the g bar and h bar which we are defining, this is in odd dimension, right? You see that will depend on the boundary, not on the whole ball. So this depends on the boundary. You see the solution depends on the boundary. Do you realize the difference here? The solution in the odd dimension and wave, in the odd and the wave, the even, sorry, the odd and the even cases. In the odd case, g bar and h bar, which are the initial data, you need to know what the initial data does on the boundary. Yeah, so it does not depend on what is it doing in the interior, just on the boundary. But here in even dimension, the formula says, you see, the even dimension, the formula says that you need to know what it does on the boundary also. Okay, this is called the Higgins formula principle. Okay, so this is called the Higgins principle. Okay, this is called the Higgins principle. So essentially think of it like this. See, if you so in the wave equation, right, this is, so let's say you have a pond kind of thing, yeah, so a small water pond or something like this, and you drop a stone in it. So what will happen? You will find out some ripples, right? You will find out some ripples. So after some times also, so this when you drop it, you will see a ripple emanating from here. It will start from here and will go on, right? Okay, so first of all it will be I mean you see a kind of wave moving on, right, or going outside. But you see after some so let's say here when you are looking at the wave, okay, you will see the ripple will be still visible here, right? Okay, there are still ripples which is visible. So basically as time moves on, okay, let's say this is the time t equals to 0 when you drop the stone. Okay, and let here this will be some time t equals to something, yeah, let's say t2 or something, yeah. So at time t2 you will of course you will find out there is some you will find a ripple here, let's say at time t2. But that does not mean that at time t equals to t1, which is between t0 0 and t1, okay, you won't see anything. Yeah? There will be still ripples, right? Small ripples you can still observe before. So you see at these points, okay, you do realize what I'm trying to say. See, so it's continuous. So basically, what I'm trying to say is, let's say if I speak, okay, in 3 dimensions. Basically, we live in 3 dimensions, right? When we speak, what is happening? If I say something to you, you just heard it and it's gone, right? You can never hear it again. You do understand? I mean, until unless you record the thing, you can't hear it again. Let's say I say hello, gone. That word is gone, right? Okay, so it's just that, I mean, it depends on the wave front, right? I mean, that what is gone. So essentially, you see, you cannot backtrack. Here, what is happening is this. You see, you have the, I mean, the propagation, okay, the disturbance. So basically, this is the disturbance, right? The disturbance which is originating at that point, okay, propagates along a sharp wave front, okay. So basically, it's just instant, it's gone like that, it's just gone, okay. But here in event dimension, so basically in the pond and all, if you look at this, the surface of the water, that's the two-dimensional object. So event dimension, it continues to have effects, okay. So basically, you see, this is the leading wave front, right? Let's say this is our leading wave front, but it will continue to have the effect after the leading wave front, the edge of the leading wave front passes also. After this passes also, it will have effects at this point or the other points. Do you understand what I'm trying to say? So you can see the ripples after a long time also. Let's look at any particular time. You look at the largest, the wave front which you are looking at, the largest wave front, let's say something like this. If you look at some particular time, let's say this is the origin of the disturbance, okay. So let's say this disturbance, so you are dropping, you have a steel pond, you are dropping something in this pond, clear? Okay, so so a disturbance is created, right? You have the water is still initially, you drop something and that disturbance is created, and due to that, the wave is moving. So basically, there are ripples going out from here, this point, clear? Okay, so what I'm trying to say is this: after this, let's say this is the leading wave front. After this passes, and after that, this becomes the leading wave front, okay. Still, you can see the effects of this particular thing, before, it continues to have. So basically, what I'm trying to say is this particular wavefront, after it moves also, it continues to have effect before, right? You understand? Okay. But in 3 dimension, so let's say, because we can't think of any dimension greater than 3, odd dimension, right? So in 3 dimension, what is happening is, let's say we just speak something. So you just hear this word and it's gone, right? So basically, it's that disturbance is not propagated along the how can I say? So it won't continue to have effects after the leading edge of the wavefront passes. Clear? After the leading edge passes, it cannot continue to have effects. It's just gone there. Okay. So basically, that is Higgins formula. Let me put it this way. So if n is odd, I hope this is, I'm not very articulate at telling you right now, I am not finding the correct words to put it together, but you do realize what I'm trying to say here. In even dimensions, you can see the ripples even after the leading wavefront passes, but in odd dimensions, let's say n equals to 3, you can't hear anything. It's just there, and after that, it's gone. Okay. So if n is odd, okay, so let's say greater than equal 3, of course. The data G and H, okay, the data, so this is mathematically speaking, the data G and H, okay, at a particular point at x in Rn, and okay, this affects the solution, okay, U only on the boundary. Clear? Only on the boundary. That is what we saw, right? Yt such that t positive and mod x minus y equals to t. Clear? Okay. Of the cone Yt such that t positive and mod x minus y less than t. Okay, that's what we saw. So basically, it depends on just that on the boundary of this thing. That's what we saw, right? You see, in odd dimension, I wrote the Kershaw Formula, this one, right? You see, it depends on just the boundary. Yeah, it does not depends on this is for a fixed t. This is a ball, but as t moves on, you do realize that the radius is changing, right? So from t equals to 0 to this actually will form a cone kind of thing now. Okay, see, t is very small, so this is the ball. T, as t becomes big and big, this gets bigger and bigger, right? That is why we are saying this is a cone. Okay, right. Now, okay, now on the other hand, if n is even, if n is even, the data G and H, okay, G and H affects you within all of C. Of course, that is what we saw. Of all of C means C is this cone. Okay, so let's say this, let's call this as C. All of C. Clear? Okay. So that is just what I wanted you to understand. Okay, so this is called the Higgins formula principle, and there's nothing. I mean, it's a very important principle. I think this was done in around somewhere around 1671 or something. Okay, around. I mean, I'm not quite sure about it, but around 1671, Higgins formulated this principle. But of course, this is not done in this mathematical rigorous way. Okay, it is done in some way physically, and later on, when we develop the mathematics for it, we just did it like this. Okay. Now the thing is, if I am asking you to solve the inhomogeneous problem, can you solve it? Of course, you can solve the inhomogeneous problem, right? Okay. How do you solve it? You just use Duhamel's principle using this. Okay. Right, now we move on to something called, so let me do it in a new page. We move on to something which we did in the heat equation also. Here we are going to do something called a speed of propagation. So we are going to show that wave equation in our setting, yes, wave equation admits finite speed of propagation. Okay, let me explain to you what all of this means, what finite speed of propagation means, first of all, in the mathematical sense, of course. Okay, so what it means is this. So the PD, so let me give you this definition first. Definition. A PD, so you see, it is nothing to do with wave equation. I mean, the definition has nothing to do specifically with wave equation. I mean, this holds for heat also, wave also, or any other equation, right? A PD, evolution equation, of course. Okay, the PD exhibits. So basically, given a evolution equation, this is the definition. Okay, so we are talking about a evolution equation. Evolution equation is equation which depends on time. Okay. Equation. Okay, so a PD exhibits finite propagation speed if the initial data G and H, right? That's the initial data in our case. So maybe I can skip the G and H for now. I will just write down the most general one. Okay. So the initial data consists of functions. So at t equals to 0, clear? At t equals to 0, the function has to have compact support. Okay. So consists of functions with compact support. Okay, then for every t positive, clear? Okay, the solution u of dot t that has a compact support. Okay, you remember in wave equation in heat equation what happens is, once the solution is positive somewhere, the initial, if you are given an initial data which is positive somewhere, that positivity gets propagated in whole of, so I mean, it does not matter how big you take your t to be, it is always going to be positive. The solution always goes to be positive. Here it may not, here it will not happen. Okay, so the solution will also have a compact support. Clear? I mean, here means in wave equation. That's what we will prove. Okay, so basically, I mean, if you want, you can just make it a little better. So basically, you say that the speed of propagation. So basically, when we say another definition, okay, another definition, the same sort of definition, but let me put it this way. So whenever we say something as speed of propagation, what does that mean? Okay, so we say the speed of propagation okay, of whatever it is, wave, heat, whatever, I mean, whatever we are working with here, okay, is less than equals to, generally what happens, generally for these problems you will see that I mean, I am always taking the speed to be 1 unit speed, but generally they assume it to be c. Why? Because that is always given as the speed of light, right? That is why it is c. Okay, for us we are just always assuming c to be 1. I mean, nothing changes. I mean, there will be extra c here, whatever the calculation we did. Okay, so that is less than c, provided, okay, that if the support SPT support, okay, of the initial functions okay, support of the initial functions is in BAR, okay, then for every t positive, okay, the support SPT of u, okay, will be contained in, so this is alternative definition, ALT, alternative definition, okay, contained in ball center at A, radius r plus ct. Clear? So basically what we are saying is this. What is speed of propagation? Speed of propagation, when we say something has a finite speed of propagation, okay, less than c means finite speed of propagation. Okay, I want to make it more quantitative, that is why I am writing it like this. Okay, finite speed, so basically less than equals c, some finite number. It means that if you start with the support, so let's say G and H has a support in this thing, G and H has supported in this ball with a center A and radius r, then the solution which you are going to get, the solution u, the support of that solution, okay, so basically I mean, roughly speaking, very vaguely speaking, the solution will be non-zero in this thing. So outside this ball the solution is going to be 0. Clear? Okay, so that's what it's called, the support. Okay, right. So it's not like a ball, it's like more like a cone, because this t actually varies, right? T becomes, from t equals to 0 to, as t moves on, it becomes a cone, right? Okay, so basically heat equation we have seen that, please remember, heat equation has an infinite speed of propagation, whereas wave equation has a finite speed of propagation. Okay, so let me put a small remark here. Heat equation has infinite speed of propagation, so it propagates, okay, for all time t. Okay, so once you have a positive number somewhere, you can't contain it in some cone, okay, so it will go on and on and on, okay, infinite speed of propagation. Whereas wave equation has finite speed of propagation. Okay. Now, see, when I say, I will explain to, we will prove this thing. This we already proved, right? Okay, this we will prove now. So, if you remember, okay, one small detail which I want you to know, I am not writing it down because this may make it a little complicated. See, these equations, when you look at for a bounded domains, it may look like this, no? UTT minus Laplacian u equals to 0 in, let's say, omega cross 0 t, capital T, something like this. Yeah? So, in bounded domain, wave equation will look like this. You see, this omega, let's say that omega is open, bounded or something, open domain in Rn, let's say, open in Rn, subset, not the whole Rn, just open subset of Rn. You can think of it as a bounded also. So, if it is smooth, generally if it is smooth, then this finite speed of propagation, this thing works, no issues. Okay. The problem happens if these, sometimes what happens is this kind of the boundary of the domain that can have some, this I am not quite sure whether you guys know or not, but just for your information, if someone of you know, it may have some fractal properties, that the boundary maybe it may look like a fractal. Okay, in those cases wave equation can have infinite speed of propagation. Okay, so please if you want, you guys can, that's just a fact for you. Okay, but you don't need to worry about all this. That's not included in this course. That is some research topic. Okay, now let us write it down. So let us prove the finite speed of propagation. So finite speed of propagation for wave equation. Clear? Finite speed of propagation for wave equation. So what does it say? If you, so you see, for now I am just taking G and H to be 0. Clear? Okay, it does not matter if you are taking something else also, it's not a problem, but anyways, this does the trick. So basically what it is saying is, initially if this is 0, okay, let's say on, it has a compact support. If you remember, you see, if the initial data has a compact support BAR, so here I am putting a compact support BX0 T0, okay, cross T equals to 0. Clear? If it has a compact support in some ball, okay, then do you think U will be something else other than 0? No. So then U is equivalent to 0 within the cone. Okay, I will define the cone. It is defined by K of maybe I can write it down here, K of x0 t0, that is defined by the set of all those xt. We already defined it, but let me do it again, such that 0 less than t less than t0, okay, and mod x minus x0 less than equal t0 minus t. Clear? So this is the cone. So this is the cone with apex x0 t0. So you understand what I am trying to say? See, you see the cone will look like this. The cone will look like this. This is x0 t0. Okay, and then so this is, let's say, somewhere here. This is the b x0 t0 minus t. Clear? And here it is x b. So t equals to 0. In this case, here t equals to 0. So this is kind of a backward wave cone, we say. Okay, we call it a backward wave cone. Clear? Okay, so let us prove this theorem first. What does the theorem says? Okay, so first thing first, we will use the energy formulation here. So proof we write down E of t. What is E of t? That is given by half of b in this particular thing. Okay, b x naught t naught minus t. For any given t, we will write it like this: u t square, of course evaluated at xt, plus gradient of u at the point xt square. Okay, d of x. Okay, this is for t between 0 and t naught. Okay, so this is the energy functional which is associated with the system with this particular problem. Okay, so that is the energy which is associated to this. Okay, what we want to do is we want to calculate what is E prime of t. Okay, let's calculate E prime of t. So this is given by b of, I'm just writing it down. I'm not doing explicit calculation of every particular thing, but you guys can do it. So this is utt, okay, plus gradient u dot gradient ut, okay, minus half the boundary now del b. So this is basically what I'm doing is I'm doing the differentiation under the sign of integration. So x naught t naught minus t, okay, and then you have the whole thing down, ut square plus gradient of u square d of s. Clear? Okay, this is given by integral b x naught t naught minus t, okay, ut. If you take the you see, you can just push it here. Okay, so utt minus the integration by parts will give you Laplacian of u dx. Okay, because u satisfies the wave equation, right? Of course, you see u satisfies the wave equation. Okay, wave equation 1. Okay, so 1 is that 1 is this. Where is 1? U satisfies this thing. Yeah, of course, use a solution of this thing. G and H is taken to be 0. Okay, so this is there. Now, okay, the boundary term plus, so here plus del b x naught t naught minus t del u del gamma of ut ds minus half del b x naught t naught minus t ut square plus gradient u square ds. Okay, so this is given by integral del b x naught t naught minus t del u del gamma. This is 0 because you satisfy the wave equation, this part is 0. So del u del gamma ut minus half ut square minus half gradient u square d of s. Right? I will just put everything together. Okay. So now, since del u del gamma, what is gamma? Gamma is the unit outer normal. I am not writing all that because those things are already known. Yeah, we are doing it all the time for this course. Okay, times ut. This particular term I want to calculate. See, this is less than the absolute value of ut times the absolute value of del u by del gamma. Yeah, that I can use the inequality here. AB is less than 2AB is less than s square plus b square. Okay, ut square. Of course with the mod, but it's okay. Half gradient u square. Clear? That is there. Okay. Now you see, if you put this thing in, let's call, I don't know, maybe let's call this thing 2. Okay. So if you put 2 in this particular term, okay, E prime of t. Okay. What do you get? You see, this thing del u del gamma ut that is dominated by half of ut square plus half of gamma t square, right? You see, this is this. Clear? So that actually gives us, therefore, E prime of t is less than equal 0. Yeah? Yeah? This is always dominated by that. So basically E prime of t is always less than equal 0. You can just write it like this. Okay. So E prime t is less than equal 0, and therefore what can you say? E of t is less than equal E of 0. Okay. And what is E of 0? That is going to be 0 for all t between 0 and t naught. You see, E of 0 is at the b x naught t naught. So basically at this apex. Okay, and the apex at one point, if you are doing integral, it's going to be 0, right? So that is why E of sorry, I just made a small mistake. So this I should write it as capital E, right? I should write it as capital E. So this is capital E, capital E, capital E. Okay, capital E of t is less than equal capital E of 0, which is 0 for this thing. Okay, once that is there, therefore what do you get? So E of t is always, and of course 0, E of t is always positive, right? See, E of t is the integral of two positive things. So basically E of t is always greater than equal 0, and which is less than equal 0. So basically therefore E of t has to be 0 for all 0 less than t naught. Clear? What does that imply? That implies that ut equals to gradient of u, not it is equals to, ut is a real number, sorry. So ut is equals to, so identically equals to 0, and gradient of u, this is identically equals to 0. This 0 is a real, this 0 is a vector. Okay, this is a vector if you want to call it. So that will actually imply that u is identically equals to 0 within the cone k x naught t naught. Okay, so what did we prove? We proved that if you start with your initial data 0, then u has to be 0. Clear? So that proves that the speed of propagation is finite. Clear? So let us end it here.